Hi everyone. In this video, I'll be talking about the machine learning lab. I'll be giving an overview of the algorithms and software demonstration. So what is ML Lab? It's an intuitive, easy to use and fast tool for training machine learning algorithms. In this demonstration, I'll present the available algorithms and I will show you how to build a neural network model for prediction of excavation wall deformations. And you can get the tool for free at geomechanica.com/mllab. These are the available algorithms in ML Lab. You can train Gaussian processes, neural networks, decision trees, and random forests. So what do you need to train a machine learning algorithm on your data? First, you need the data preparation. You need to normalize the output of the data. So if you have like 3 columns of input and 1 column of output, you need to make sure that this output falls between 0 and 1. This doesn't mean that if you have values larger than 1 that you cannot use the program. All you need to do is you normalize your data. So if you have like say the range of your data is between 10 and 100 or 10 or 150, you can divide all your data by the maximum output value so that your data falls between 0 and 1. If you have negative data, you need to work this on those two. So you need to make sure that all your data are larger than 0. No negative data are allowed. So, and this is done by shifting your data points by a value equal to the least or the minimum negative value. So if you have like says data between -5 and 20, so you need to shift all your data by 5 so that your data falls between 0 and 25. Then you would need to normalize the new data and divide everything by 25 so that your data falls between 0 and 1. In terms of input, large ranges should be avoided. They lead to slow learning process. So in this example, let's say if you have data this 1 over 1000 or over 10,000 to 100, you need to use something like a logarithm or a square root or root of higher order in order to bring your data ranges together and avoid the wide range. Next, after you finish your data, you need to import your data into the program. The data needs to be in CSV format. Excel formats are not allowed. So before you import your data, make sure it's an CSV file. Then you would need to do hyperparameters tuning for each model. If you are trying to train a neural network, you need to adjust the epochs, the learning rate, the layers, and the neurons. If you're doing the random forest, you would need to adjust the number of trees, the depth of each tree, and the feature split of each tree. Finally, you can now train your data and see the output. What you would need next is, of course, you need to post-process and evaluate the output and make sure that the error falls between in acceptable ranges. If the error is too large for you, you would need to retrain your model with different hyperparameters to see what happens to your data or to your output. So this is an example of how to train a neural network algorithm on deep excavation data. So deep excavation is a problem in geotechnical engineering that's challenging to predict the lateral wall deformation, delta H sub H here. And this is complex. This is a complex problem because of the number of inputs that are needed to evaluate the lateral deformation of the wall. So what we are going to do is train a neural network model based on case histories, so actual displacement or wall deformation data. And we are going to use input, it's the wall height, stiffness, wall embedment, the depth of excavation, the soil properties, the depth to the hard stratum from the base of the excavation, the number of struts and their spacing. And the output of the model would be the maximum wall deformation. The data we are going to use is available in Kang et al. 2007 and is provided in the zip file as excavation data as an Excel sheet. These are the actual data points. We have the construction method here. One is for top-down and 2 for bottom-up approach of construction. We have the number of excavation stages, the excavation width, final excavation depth, wall length, and to the output, which is the lateral wall deformation normalized over the height of the excavation. Now you would see some data points that are missing. For example, the zeros here are not, doesn't mean that the modulus of the stiffness of the wall was 0. It means that this data was missing. Now you can do something better than this in order to replace this 0 value with something that is reasonable with data. You can use linear regression, you can use statistical analysis methods, averaging, anything that you could use to fill these data points. There are methods for those, but they are beyond the scope of this presentation. So what we are going to train is train a neural network to take columns A to M as an input, and then give us the column N as an output. But before doing that, we see that here these data points are larger than 1. We'll see why we need to normalize these data points before training, because the algorithm would have difficulty in predicting those values. So the error would be very high in this area. So it would be better to normalize the data before training, but we will see what will happen in the next slide. If we look here, we see the correlation matrix for the lateral wall movement with the different variables. You can see that lateral wall movement is inversely correlated with most of the variables. That means if an increase, an example for an excavation stage would lead in decrease in the lateral wall deformation. However, there are some variables, interestingly, that are positively correlated with the lateral wall movement. For example, the excavation width, and also we can see the average spacing of the struts are positively correlated with the lateral wall movement. Now we can take a look at how to train a neural network for the purpose of predicting the lateral deformation of a wall. So this is the interface of the program. Here you can start here by having a training file path. You will choose from the CSV file here. So, and I'm choosing now the data for my excavation, and you can see that this is the file path. Next, you can define the number of inputs, which are 13 in our case, and the number of outputs, 1. And then here you will find the tabulated pages or tab pages. Here you find the graph. After you train, you will see the performance of the network here. This is the tabulated values for the graph. And the most important one we need here is the neural network hyperparameter tuning. So this is for the definition of number of layers and the number of neurons for each layer. This is for the learning rate, the epochs, and then if you want to try advanced setting like have a control on the transfer function used and the loss function, you can select it from here. Now, if I start adding the number of neurons, let's say 10 neurons, then I will have one input layer that takes the input from your data, and one hidden layer with 10 neurons, and then one output layer. This is the current. Now we have everything ready. We can click on this button here to start training the model. I adjusted my neurons a bit. So if I click here, it will first import your data, run through the data with epochs, and then will produce the graph for the training. If I increase the number of epochs, this might take longer. So for example, if I have 200 epochs and start training again, you can see the progress bar and so on. Of course, there are ways to improve this prediction. If we look at the performance curve, we see that there are points are way off the prediction line, the perfect prediction line. So there are ways to improve. For example, you can increase the number of neurons. You can use any number until you get the desired accuracy. Keep in mind that neural network can learn any data. So if you have data points that are hard to predict, you can hard code it to have as many neurons as you want, and the neural network will finally adapt. But there are more efficient ways to do this by increasing the number of layers, which will allow the neural network to learn from the nonlinearity in your data. You can increase the number of epochs and the lower or increase the learning rate to improve the output of your neural network. Let's take a look at some of the trials I have tried in my training process. Here you can see I have a large neural network with as many layers. This is the start of the project. I just had as many layers as I could, and I have a very large first layer. You can see the performance here is okay in this area, and then it starts to deviate from the perfect prediction in this area and this area. These 3 points will never converge. These 3 points will never come here. Why? Because as I told you before, you need to bring down the order of your data between 0 and 1. So, and this is what I will do in the next slide. So here, as you can see, I reduced the number of layers to 4. Each layer has 33 neurons. I have 5,000 epochs with a learning rate of 0.01. What happened? The data got a little bit scattered in this area, but then I got very good prediction in this route or in this area. This is my final training, and this is the best performance I got. So it's just similar to trial number 2. However, I used 10,000 neurons in the first layer, and then I increased the epochs to 10,000. Of course, my data is already normalized here, so I got a perfect prediction even in this zone, and I got very good prediction in this area. After training, now my data is ready for post-processing. All I did is I used my original data and then added columns for the predictions normalized, which is the processed prediction. You can see the predictions are always between 0 and 1. Then I readjusted my data. So I multiplied my predicted normalized by the maximum here, which was divided on in the training process, for the training process. And then I got the new prediction and compare it with the original data prediction, and I calculated the errors. This is the errors calculated at for different outputs, and you can see that the maximum error is around 1.7%, and the minimum error, which is negative 4%, which means that the maximum error will overpredict by 1.7 and the minimum error will underpredict by 4%. So let's recap what we have learned so far. Training is an iterative procedure. It's a trial and error procedure. So you have to start with a first draft of a neural network and then adjust and improve on it. Training a large neural network on large datasets can take hours or even days. I have some neural networks that took days to train to get a good output. It's better to train on small batches. If you have a large data point, use the advanced neural network with batch training. And you need to prepare your data. Numbers should be always decimals. Do not use a comma in your data. It should always be in this format and should be always normalized, no negatives. And you can see the manual for more details on how to prepare your data. You can also try other models and compare the output. We have the random forest, the Gaussian process, and decision trees. The random forest and decision trees were originally developed for classification problems, but they can be used for regression and have been used for regression purposes. After you finish training, you will notice that the program will save the neural network and will give you the file path on which the neural network was saved. So you can retrieve this neural network and use it for further application, as we will see now. Now we will use the trained neural network on practical application. So this is the real case study, as we will see later. It's for an excavation that is 12.3 meters deep, and this is the soil profile for the excavation. So we need to support this excavation and provide an initial design to see how we can prevent large lateral wall deformation. So what we have, the width of excavation is 34 meters. We have a 60 centimeter thick concrete diaphragm wall that will be used, and the construction stages will be 5 stages. What we need to optimize is the wall embedment, the number of strut, the construction method, and the wall section. Additional info, we have the unit weight as a function of depth. It goes from larger than 19 to below 19 here, and then goes straight. And then for this layer, it's 21, and then it goes back to 19 for the remaining layers. And this is the undrained cohesion normalized over the effective stress for this type of soil. This is an example use of how to perfectly use the neural network. Now we can generate an Excel files with the following input. We have two diaphragm wall sections, 0.4 meter thick and 0.6. We have multiple length for the wall. Keep in mind that the length of the wall goes beyond the excavation depth. So we have 16-meter wall, 18-meter long wall, 20 and 25 meters long wall. We also proposed the 3 and 4 struts. Based on the number of struts, you can divide the excavation depth by this number to get the spacing for the struts. So this is the cases or the design proposals that we have. Some things are constant. For example, the total excavation stages is 5. Construction method, we are using number 1. And final excavation depth is always a constant. Wall length is a variable. You can see that we are beginning by 16, then from 18, 20, and 25 meter long walls. Wall thickness, the stiffness of the wall, we are using concrete, so we can get this easily by multiplying the stiffness of concrete by the moment of inertia based on the thickness of the wall. We also have the number of struts and their average spacing, the depth to the hard stratum. I took this from the soil profile and the original problem, and the percentage of clay over the wall, and then we will divide the stiffness of the wall on the effective stress and the shear strength of the soil on the effective stress. So I prepared this table to use it for the prediction of the proper design for the wall. Keep in mind that you need to make the order of the inputs as the same as the order of the inputs you used in the training. So for example, my first column was construction method. Here, my first column should always be construction method, and so on. Excavation stage is the second in my training, so it should be the second in my application here. Now I'll open the program again to see how to use it, a safe neural network for the prediction. So if you previously trained the neural network, you would find the file path to the neural network somewhere at the end of your log of the training process. You can copy this path and put it here directly in the save neural network file path in this area. And then I have prepared the design alternatives as CSV file, and I put it in this path here. And then I can use this button to use the trained neural network to predict my design, the performance of my design alternative. If I click here, it will fill the table, which is called prediction, the third tab page from the tab pages. These predictions can then be copied to my Excel sheet to see how the deflection would become after processing the data. So now I copied the neural network prediction into the actual table that I prepared before for the design alternatives. And we can see here this is a neural network prediction, and this is the multiplied by 2.1, which was the maximum value before, and this again multiplied by the height of excavation, which is 12.3, and we get the results. And we can see that our minimum displacement, maximum allowable deformation was 0.06 meter, and here we have lateral wall deformation of up to 0.23 meters for the alternative number 1, which was 0.4 thickness wall with 3 struts, and spacing between struts was 4.1. Okay, and we see the green ones are the feasible design alternatives. You can see that the minimum deformation was at 25 meter long wall, 0.6 meter thick, and 4 struts. Also 3 struts is a feasible alternative. So we can choose this design alternative and further investigate what we can do with it to make it comply with design codes. So now I evaluated around 15 design alternatives in one go. I didn't go through any calculations. My predictions are based on actual databases, not empirical values. So neural network can help you in this regard in many applications similar to this one. These are the results we got. We got a neural network prediction. As you can see, these are normalized values, so I need to multiply it by the maximum. data point that we had before, which was 2.1. So I need to multiply this by 2.1 to get this value. And then we need to multiply because the data is normalized again on the height of excavation. This was in the database. We need to multiply this value, the percentage, by the height of the excavation to get the final lateral wall deformation delta HM. We can see that these are the results. So let's see what we have here. Again, here we have the design alternatives. We have 25-meter thick long wall, 0.6 meter thick, 3 to 4 struts, and the expected results of the feasible alternative. This configuration here is for the 0.07 meter displacement, which it's 7 centimeters, which is very close to the 6 centimeter that is required by design. These are okay designs. We can make sure by hand calculation to see if this 0.09 deformation will hold up in calculations, or if it's just an output of the neural network and the calculation can be further improved. So we might need to consider these points also, even though I got this configuration here. The 9 centimeter deformation was for a 60-meter wall, long wall, and also you can use 80-meter wall when you will get the same lateral deformation, and the 25 or 20-meter long pipe has a deformation of 0.08 meter, which is 8 centimeters. So you might need to consider these alternatives in your design. Finally, we can summarize the analysis results as we can exclude all 0.4 meter thick walls because they didn't meet the criteria, and this exclude 8 cases that we don't need to investigate. And again, the next step is to investigate the feasible alternative using the rigorous hand calculation and finite elements maybe to confirm these values. So how does the neural network prediction compare to the actual case study? So as I said before, this was an actual case study presented in Deep Excavation Theory and Practice, which is a very nice textbook on deep excavation. In the actual study, they used a 0.6 meter thick wall, which was what we found in our analysis, 23 meter long diaphragm wall. We are close, we have a 25 meter, and they used 4 strut in the analysis. And the lateral wall movement was measured, this is a measurement, not a calculation, at 60 millimeter. Compared to our results, we have 0.6 meter thick wall, we have 25 meter long diaphragm wall, and we have 4 struts. So we are 2 meters above the 23 meter threshold. And the measured movement, again, is 6 centimeter compared to 7 centimeter analysis. We can say we are not far off from the actual case study. And I should mention that this case study is not used in the training data. So the neural network never saw this data in the training and was able to predict with a very close lateral wall deformation to the actual measured, not calculated, measured lateral wall deformation. Again, this chart here is from the book, and we can see the maximum lateral wall movement occurred at 60 millimeter, which is 6 centimeters, at depth of about 11. And this nice chart shows us the progress of the excavation with stages. If you want to do something similar like this, if you want to calculate the lateral wall deformation per stage, you can define your problem as a stage-by-stage problem. So the first stage will be like 2 meter deep excavation, and you can define your wall geometry, and number of struts here would be 1 only in this case, and then continue analysis stage by stage to make sure that each stage have a good prediction compared to the case study here. So, to wrap up, what we learned so far from using the neural network, the trained neural network gave a good wall configuration and estimated wall movement, very good compared to the actual used wall. As I mentioned, the case was never used in training. The neural network was also able to predict reliably. And I should always emphasize on the need to comply with codes. This is not a final design. You need to go and check the configuration you got from the neural network and use the codes in your country to make sure that the design of the wall meets the criteria mentioned in the design codes in your specific country. So, but how can the neural network help us, or how did the neural network help us? Of course, we had 15 design alternatives and we excluded around 8. We have like 7 feasible results, feasible design alternatives that we can use to make sure that they comply with code and further investigate the actual deformation from the calculation, and then we can go to the field and do the excavation. But the neural network cannot be used as the final design procedure. That's it for today. I hope you enjoyed the presentation and learned so much from it. And I should talk about the use cases for the neural networks or machine learning algorithms. You can train them on the data that you have internally in your company for the actual cases that you calculated, bearing capacity, settlement, and anything you have. You can use it and train the neural network model to predict it, to be able to predict. And then you can use the neural network to help you design. This will reduce the time needed to finalize the design. So if you have a foundation case of the pile foundation, you don't know the length of the foundation, you don't know the geometry, you don't know the material of the foundation. Should I use an H-beam pile or should I use a drilled shaft? All these can be programmed into the neural network to be able to predict the performance of the pile based on the soil profile, and everything you have in your data will help the neural network predict the proper design. Then after the neural network give you a good design, you need again to confirm this design with code. Again, that's it. I hope you enjoy building machine learning models with ML Lab, and make sure that you visit our website to get your copy, which is free now.